That's the clicker over there.
Nice.
Okay. Go ahead.
Thank you. Hello, everyone. Welcome. My name is Juliano Laganá. I'm a staff engineer at Moduli. We're a machine learning consultancy company. Maybe you've seen our booth downstairs. We do some really cool stuff. We have a great team. We're hiring. If you haven't passed by, I recommend you take a look. I'm also a part-time entrepreneur. I founded Juliano Labs, the company where I run educational content and workshops on topics like these and clear thinking and so on. So today's talk is about machine learning debugging, and I want to start somewhere familiar to, I think, everyone here. Debugging is hard, right? I think hopefully everyone agrees with this sentiment, right? And it's at least as hard as writing the code in the first place, usually considerably harder. How harder depends on the type of software engineering that you're having. And I truly believe that among all the types you can have, machine learning is among the hardest ones for multiple reasons, right? First of all, we have so many failure points, right? It's not just code that can be wrong. It's also the data, the model architecture, the optimizer that you chose, the hyperparameters. Everything can break your code in silent ways, in subtle ways. Not only that, but there's this cake principle. Google introduced it, which means changing anything changes everything, which I guess most of you can relate to. Imagine a pipeline that you have, maybe pre-processing, training, evaluation. If you change, say, one of your features, probably everything downstream will also change accordingly, right? You get a different optimization trajectory, you get a different final model with different importance weights for each of the features, with different final performance and inference behavior. So this makes it hard for us that when you see a symptom, you might not immediately know where the root cause might be, because there are so many possible failure points and they're all kind of tangled, so it makes it really hard to debug that. We also use a lot of black boxes, especially in the era of LLMs, right? Those also make it harder to diagnose and figure out what's actually going wrong. And lastly, as stochastic gradient descent, optimizers in general, they seem really good at optimizing around our mistakes, right? With that I mean, imagine you're doing something wrong in the pre-processing. Maybe you were pre-processing images and you unintentionally swapped some image channels. And then when you wanted to drop maybe the alpha, the transparency channel, but you dropped the green channel for some reason. If that doesn't cause a dimension mismatch or some type of crash downstream in your pipeline, SGD will just happily optimize that away for you, right? You'll see a loss going down, you'll see performance going up, and you'll be none the wiser. So this creates the situation where bugs are tricky to find, to know where the root cause is, and sometimes they're even silent, so you can't even know where they're coming from. Even though that's the case, and I think most of you that actually practice this can relate, you see no classes, books, or frameworks on how to do this properly. We, as a field, we don't seem to be spending much energy, much time thinking about how to improve this and how to teach this to new people joining the field. And this creates a problem because it means that every practitioner will have to learn this on the job, on their own, by trial and error. Maybe you've been lucky, and the first bug that you've seen, the first really hard bug in your pipeline, you had a colleague to walk you through to give you some ideas. Maybe you weren't. And that creates a situation where I see practitioners, I see myself a few years ago, and a lot of colleagues gravitating to this approach that I call the bag of tricks approach. So let's talk about that a bit. First of all, let's talk about what a trick is. So imagine that you're working on your machine learning project for a while, and you're building the pipeline. You're creating the pre-processing, the training, the evaluation, and so on. And that's working well. Maybe you see a few bugs during that development process, but nothing major, right? You see maybe a few value errors, key errors, dimension mismatches during the training. Nothing really crazy that usually you see the bug, it tells you kind of where to start looking, you debug, doesn't take that much. Maybe fixing the core root issue could take time, but the diagnosing, the investigation doesn't take time. Until it does. Until you're faced with a situation where you see a symptom telling you that something is wrong, but that symptom tells you nothing about where the bug might be coming from. Like, imagine that you have a pipeline that trains a model, doesn't crash, doesn't do anything, but final performance is really bad. Or maybe final performance is good, but inference performance is really bad. Because of the many failure points and because it's so tangled among them, it's hard to even know where to start looking. And if you don't have a method, if no one told you like how to even start looking for these issues, you probably just debug for a very long time, right? I remember my first few bugs in this, and it was just stumbling around in the dark and just trying to see, oh, maybe the pre-processing is doing something wrong. Let's step through the entire pre-processing code and see what's happening there. Or maybe it's something in inference. Maybe the packages have a mismatch or something like that. All of that takes a long time. And it's going to take hours, maybe days, depending on the pipeline that you have, how complicated it is and how subtle is the bugging that you're looking at. It might take you even weeks, right? But we are determined people. I believe that to work in machine learning, you have to have some level of determination, some level of stubbornness to push through these obstacles. So even though we don't have formal training in this, you will eventually find the root cause of the symptom you were observing. At that point in time, when you find the root cause, because it was such a painful and time-consuming experience, I can already tell you, your brain will create a very strong connection between the symptoms that you observed and the root cause you found in the end. If it was inference performance being bad, the symptom, and later you realized, oh yeah, we're leaking target labels into our features, your brain will create a very strong connection between these two things. So much so that the next time you're working on a project, it might be months later, different project, different context. If you see the same symptom again, your brain will immediately scream at you, did you check the pre-processing? Are we maybe leaking labels into our features, right? And this is one trick, but you keep working with ML and you keep developing your skills, working on different projects and contexts, and you develop new tricks because you debug more and you learn more links between the symptoms and the root causes. And that's when you get into this approach that I call the bag of tricks, which essentially just means whenever you see a new bug, you reach into your bag and you say, hey, have I ever seen some symptoms like this before? Are there any root causes that might explain the thing that I'm seeing here? Which is vastly better than just stumbling around in the dark, having no idea where to even start looking. But it still has many problems. It still makes us spend a lot of time searching in the wrong parts of the code base. Primarily because of two problems. The first problem, which is not really a problem of the approach, but it's a problem that I see in us when thinking about these things, is that we tend to systematically underestimate the cost of checking hypotheses. So if I see a symptom, inference performance is bad. And I reach into my bag of tricks and I get a trick that says, hey, check the pre-processing. Maybe we're leaking target data. In my head, that sounds like, yeah, let's do that. That's going to take a few minutes at most, maybe an hour. Probably not, right? If you've done this a few times, you realize later, well, actually, no. We're talking about, at least in real-world scenarios, we're talking about very complicated pipelines with a lot of code, especially the pre-processing step. That's probably the step that is among the most complicated ones and hard to understand if you're coming from an outside perspective, right? There's usually lots of data to be pre-processed, maybe some feature engineering happening. Maybe there's business rules in the middle, and maybe it wasn't even you that wrote the code. Maybe it was another colleague, or maybe you wrote, but in the meantime, everything changed, so you lost all the context. All of that will contribute to it not being as easy as you imagined to go through that code. Not only that, but if you're checking a hypothesis like, are we maybe leaking target data into our labels? That can be done in so many different subtle ways. So to be able to go through the code and say we're not doing that, you have to have a pretty good understanding of the code. Maybe you do have to like call a colleague and say, hey, why are we doing this? Or maybe call the stakeholder and be like, do we really need to do this? Does this make sense? How will this look in inference? Is this leaking data or not, right? So what initially seemed like maybe a few minutes, maybe 1 hour, it can quickly escalate to many, many hours of work. And that alone is already problematic, but maybe you're not like this. Maybe you're more pessimistic. And maybe you're like, no, I know this will take a long time, but Juliano, hey, here is like a real shot at finding the bug, right? We saw symptoms, we had no idea, and then someone comes and say, if this is happening, that would explain the symptom we're seeing. So it's natural to feel like, hey, this is a good probability of actually finding the bug, right? It doesn't matter if it's going to take a few hours or more, maybe even a day. If it's going to fix the bug, if it has a decent chance at fixing the bug, we should do it, right? And the problem is, I don't think it has a decent chance of fixing the bug because of something called availability bias. Availability bias is this mental shortcut that us humans do, where when we want to estimate the probability of something happening, we try to recollect all the times that has happened to us in the past. So based on how easy it is to remember that happening, how available that is in our memories, we assign higher or lower probability to that event happening. Which day-to-day life is great. It helps us navigate all sorts of situations where you can estimate probabilities rather well. But once the probabilities start getting very small, this becomes something that will mislead you. When probabilities are small, for instance, when we're talking about what kind of failure point caused this issue, then you're probably going to overestimate the probability of the things that did happen to you, all the bugs that you did see, and you're going to think that those are more likely, and underestimate the probability of all the other things that never happened to you. Imagine how many possible ways a pipeline can break that make inference performance be bad. I mean, dozens, hundreds, maybe thousands, right? So if you look at a single one and say, hey, I think we might be leaking labels into our features, the prior probability, the base probability for that should be very low. And hence, when you join these two problems together, the bag of tricks approach, or variants thereof, make us be looking at the wrong parts of the pipeline and investing way too much effort into these hypotheses. So here's the gist of it. We, as machine learning practitioners, we have to deal with these very complicated systems that can break in complicated and subtle ways. At the same time, we are using very rudimentary tools that once you look close enough, you realize we can probably do much better than this, right? And at the same time, we pretend like this is okay, like this is not harming us, that this doesn't cause problems for the field, right? This is why the title of this talk is called We Need to Talk About Machine Learning Debugging, because we do. We need to take this more seriously, right? It's affecting us at many different levels. Like first, just the personal level. We as practitioners, this is the painful part of development, right? I'm yet to meet an engineer that comes to me and say, hey, Juliano, I built this pipeline, nothing works, I have no idea where to even start looking, and I'm loving it. That's not the experience that we like about it, right? Second, on a more organizational perspective, we fail to have reliable estimates of budgets, how much time and money this will cost. If you scope a project to, say, 2-3 weeks, and in the second week, you find a bug that takes you 5 days to debug, it's going to be hard to keep that promise, right? You're going to have to sacrifice either cost, time, or quality. One of them has to go away. And lastly, I see this as really contributing to the stereotype of the crazy wizard. We're a bunch of crazy wizards with our cauldrons, and we just throw stuff in, and sometimes we make magic with it, sometimes it blows up. We don't know which is which until it happens, which is a passable archetype for maybe research, because you do have to push the human knowledge, the boundaries of human knowledge. But for industry, this is not the image that we want to pass. We want to be professionals that develop high-quality solutions within the budgets that we promised consistently, right? Cool. Good on time. So let's talk about the solution. I'll start off by saying I don't have a silver bullet, unfortunately. I won't tell you something magical that will make all your debugging sessions last just a few minutes. But I think I have something that could be a good starting point for us. And it comes from just asking a simple question, which is, are there any other fields that have to deal with the same problem that we do, and that have maybe been doing this for way longer than we have? Can we learn from such a field if there is one? Very, very fortunately, there is a field that has to deal with the same problems, if not worse, and has been around for way longer than we do, which is medicine. The human body is probably the most complicated pipeline you could ever dream of. It has all the problems we listed and more. Everything is tangled. There's so many failure points, so much tech debt. Imagine what millennia of natural selection did to these types of pipelines, right? And yet, doctors are somewhat able to go from symptoms to root cause fairly efficiently, right? So let's try to take a hint from doctors. Is there anything there that we might be able to translate into machine learning? And I want you to imagine this thought experiment with me. Imagine that you go to the doctor's appointment because you woke up one day and you're feeling dizzy, just out of the blue. Never happened to you before. So you feel like, yeah, I should probably go check that up. So you get into the doctor's office and you say, hey doc, I'm feeling dizzy, woke up like this today out of the blue, can you help me? And then the doctor just sits there and like stares at you and thinks very hard. And he's like, I know what you have. I think you have meningitis. Because 3 months ago, there was a patient that came in with exactly the same symptoms that you're describing, and it was meningitis. So I suggest we just do a lumbar puncture to try to rule that out, and then we take it from there. How would you feel about such a doctor? I mean, I would probably never come back to such a consultation, right? And I would not do the lumbar puncture. I mean, it sounds kind of crazy that they would just jump at a hypothesis like that and prescribe something that is both costly and painful to me and time-consuming. I would not just trust that doctor, right? And hopefully it's obvious the counterpart here to what we do in machine learning. This is what we do. When we jump to see the preprocess, if the preprocessing is leaking targets into features, this is what we're doing. We're scheduling a lumbar puncture. We're jumping to a hypothesis. So how would we expect a good consultation to look like instead? I would expect something like this. I go in with a complaint and I say, hey doc, I'm feeling dizzy. And then they would just shower me with questions, like straight up, like, when did this last start? Do you have any other symptoms? Do you take any medications? Anyone else in your family? Have you been abroad? Have you traveled? Like so many questions that would just so much faster and efficiently will find like data, valuable data to the doctor, right? And then after that, after a bunch of questions, they would start doing some cheap tests. Like they would maybe take my temperature, maybe they would take my pulse, right? Maybe do a blood sample, something really quick. And maybe especially if it's dizziness, maybe they'll ask us to do something like, oh, hey, can you stand up and touch your nose with both of your fingers? Those types of things that look silly on the surface, but when you think about it, it's actually really smart because it's super cheap and it's testing multiple parts of my pipeline, my body, at the same time. If I fail to do this, that will give like key information about what kinds of things might be happening. And if I manage, it would also perhaps not rule out, but really lower the probability of other things that might be happening. So what can we learn from this simple thought experiment? Well, two things. First, costly experiments, they need to be justified by enough evidence. If I go to a doctor and they shower me with questions, do a bunch of experiments, tests, and then later they say, hey, you know what? All of this data is actually pointing towards perhaps meningitis. And if it is meningitis, we need to act quickly, so I want to schedule you for a lumbar puncture. I would be like, that sucks, but sure. I would trust that doctor way more, right? Because now the costly experiment is justified. It doesn't feel like it's jumping to a hypothesis, right? It's not just availability bias speaking. It's actual data speaking. And if we're not running costly experiments, what we should do instead, at least in the beginning, is run these cheap, high information tests that doctors do, right? This is how we should be thinking. So what I'm proposing here is somewhat of a mindset shift. This is how our debugging sessions currently look like. On the x-axis, you have time. On the y-axis, you have uncertainty over where the bug is and the cost of the experiments you're going to run. Uncertainty starts high because when you see the symptom, you're like, I have no idea where the bug is. So uncertainty is really high. And you're going to run experiments that try to reduce that uncertainty. And the problem is, if we do a variant of the bag of tricks approach, what we're going to do is every single experiment is going to be somewhat time-consuming. Maybe they're not all time-consuming in the same way, but expected is going to be very time-consuming. And they're all going to be high stakes in the sense that they're testing for one hypothesis. If you find the root cause in that hypothesis, you're golden. Uncertainty drops to 0, you found the bug, debugging is over. More likely, you're not going to find the bug. And then you end up with information like this. Oh, now I know that the bug is not caused by an unintentional swap of image channels, which doesn't tell you much about where else it might be, right? Maybe it took you like hours of looking through the pre-processing code to rule that out, but you still can't rule out that there's another problem with pre-processing, right? And you repeat this process over and over, checking one hypothesis at a time until you find the bug, because maybe you got lucky, or until you run out of tricks in your bag, and then you resort to something like just stumbling around the code base and stepping through every line of code. This is what we currently do. Here's what I think we should be doing instead. Just like before, uncertainty is really high. We can't change that, right? We don't know where the bug is to start with. But the thing we change is that instead of running these single hypothesis checks, we run smart experiments that test multiple parts of the pipeline at once in a cheap way, just like the doctor. Once we do enough of these, then uncertainty starts dropping really quickly. It won't ever drop instantly to 0 because you're not checking single hypotheses, but precisely because we're not being eager trying to go to hypotheses already, uncertainty drops much quicker. And as it drops, the hypotheses start forming, just like for the doctor. And when hypotheses start forming like this, then it's not availability bias. The data is pointing to them. And when that happens, then we're actually justified to run costly experiments to test these hypotheses. If all the data is pointing to there's something wrong with the pre-processing, maybe we're leaking data, maybe something else, then absolutely spend hours tracing through that code until you actually find the problem, because now it's justified. So how can we do this in machine learning? We already know how to do the time-consuming experiments. Let's talk about the smart, cheap experiments. And we can start with just the questions, right? Just like the doctor asks you, hey, when did this start happening? We can ask the same thing from our pipelines. If you're mildly disciplined with using Git in your projects, it's very easy to just go back a few commits and see, hey, did we see the same symptom before? And when you find a commit that doesn't have the symptom, maybe do a git bisect, and that will tell you like a few lines of code that have changed, maybe dozens, maybe hundreds. Think about, first of all, how quickly you can do that. Oftentimes, if you're good enough with Git, that will take you not very long. And now think about how much information that gives you. You went from, I have no idea where the bug might be, to, I have a very strong prior that it's related to these lines of code. It won't necessarily be in the lines of code, because sometimes it's a pre-existing bug that's just waiting for the right conditions to surface. But oftentimes it is in those lines of code. And so it's a really good starting point that you get for free or for very cheap, just like the doctor. Other questions you can ask, like things like, are there any other symptoms? The translation to machine learning world is, do we see anything weird in our pipelines? Are we producing any nuns or infs or warnings or anything like that? And most frameworks have a good way to give you this information. PyTorch has a diagnostics mode that if you turn on and then you run training or evaluation or whatever, it will tell you exactly when nuns or infs show up which is a great experiment to run and also very quick. And also just looking at other metrics. Sometimes we get so tunnel vision into one thing that's not working. Say maybe training loss is going down, but in a weird way, and we just stop looking at everything else that we have available. And sometimes we don't even save all the information that we could save. For instance, maybe your loss is a sum of 5 different things. Also log the individual things. That will help you a lot when things go wrong. So you have more data to go on. So these are the equivalent questions we could ask. And you could go further into this direction, right? But let's talk also a little bit about the types of experiments that we can run. I don't have an exhaustive list because it's very pipeline dependent, very project dependent, what's going to be fast or what's going to be slow for you. But I have a few that I hope will illustrate the mindset you should have. What we're looking for are these types of experiments that are A, are cheap to run, and B, test multiple parts of the pipeline at once. We're thinking this, but for a machine learning pipeline, right? Here's a very simple one, stole from Karpati. Training on a single batch. What does that mean? If your model is having some training issues, some problems like that, this is usually a really good diagnostic you can run. Can your model train without sampling new data from your data set every time? You just fix that data. Why is this a good test? First of all, it's super cheap. Hopefully, this is a one-line change in your data loader or somewhere, maybe 3 lines of code. So your time is going to be very cheap. Then you need to let it train, which it's not your time, so you can at least go do other things like the git bisect I mentioned. Or it also will probably converge way faster than when you train on the whole data set. So cheap it is. Now, what do we get when we run this? We get a simplified setting where we know what's supposed to happen. If you effectively just fix on one batch of data instead of the whole data set sampling, then you're not doing SGD anymore. You're just doing regular gradient descent, which for most loss functions you can have. If you tune the learning rate appropriately, you expect the loss to go down. Not only that, for most problems you're dealing with, your model will have more than enough capacity to just memorize those labels, right? And if it does memorize the labels, so you expect now the training loss to go down and to its minimum value. Run that. Does that happen? You'll be surprised at how many times you have a working pipeline where that's not true. For some reason, you don't get the minimal level, or for some reason, it doesn't decrease like you expected. And if it does, so if it doesn't, you're golden. If you fail that test, you already know, hey, you went from I have no idea where the bug is, and I don't even know where to start looking, to I have a pretty good idea it's related to this part in training, loss computation, backprop, gradient descent, right? Even if it passes the test, that gives you so much more information on a failed test than if you were to say check for a single hypothesis. Because if you manage to do that, you don't rule out any hypothesis, but you're that much more confident that, yeah, at least the training part, the optimization part is kind of making sense. We tested a little bit and it's doing the right thing. And then you can progress to, say, training on 2 batches of data, which is actually fundamentally different now, because the model doesn't need to only learn something about the labels. It needs to learn something about the input data so that it can memorize which one is it looking at. So it's testing both, can my model look at the input, and can my model look at the output? And then you progressively increase that. Once you fail, you're golden, you're in a simplified setting. If you succeed, you're that much more confident that at least that part of the pipeline seems to be working well. Another one you can do, similar direction, but in a slightly different twist. Let's say you have something like binary classification, right? And let's say it's 50-50. So you have your features, you have your labels. Go through your data set and just randomize the labels. Flip a coin. That's the new labels that you're going to train on. If you train on that, what do you expect to happen? Your model won't be able to learn anything, right? It's a hopeless task. It should absolutely not beat a random baseline. If it beats a random baseline, you probably are leaking some target data into your features. Or there's maybe something wrong with how you're evaluating the model or computing the loss, right? And there's so many more examples that we could give here. we have things like setting your features to 0 instead. So same thing, maybe it's binary classification, but this time set your features to 0, don't touch your labels. Train on that. What do you expect to happen? Well, you would expect that it's not able to learn anything about the input. So the best thing that your model can do is just learn the underlying class distribution, right? So let's say that the balance is 70-30. You expect your model to just learn to always predict 70-30, right? Another thing you can do, adding canaries to your data. Canaries are these placeholder values that are maybe very easy to find in your data set, and you just add a few of them in your data set. Can you trace what happens to those samples as you run pre-processing on them, as you run the training code, as you run the evaluation code? What's the final performance in these placeholder values? That's like the counterpart of those tests where you drink some contrast and then they look at your body to see how it processes it, right? So much information so quickly. And again, not an exhaustive list. I hope this illustrates the mindset, right? Simplified setting, testing multiple parts of the pipeline. We're not testing single hypotheses. Having said that, you can also probably brainstorm with your AI here, and if it has available knowledge of the code base. You can also, hopefully, in a few years, we'll be able to offload most of this to AI. Right now, simple bugs, or at least simple code bases, you can already say, hey, help me debug this. And it will have a decent success rate at finding the bug. Fixing the bug, probably not yet. But finding the bug, it's helpful. And right now, the place where I'm having the most success with is actually asking for experiments, ideas on how we can test in a cheap, simplified setting. Just said a lot of information at you, so let's do a quick wrap-up before we finish. We started with debugging is hard. It is. Machine learning debugging is probably among the hardest ones we can have. We put it at least at very hard. And I think we're making it harder than it needs to be, right? We don't have currently any resources on this. We don't teach people how to do it. They just learn by trial and error. That makes us gravitate to a bag of tricks approach, which is problematic because of the two things. We underestimate the time it takes to check the hypothesis, and we suffer from availability bias. I propose this new approach as our first step as a field, inspired from medicine, a field that has to deal with these types of problems for a long time. The first takeaway is we need to run cheap experiments that test multiple parts of the pipeline, and only after that we run the experiments that we're used to, that actually are costly and check specific hypotheses. So lastly, the idea here is we want to move from a one-by-one hypothesis testing to a more structured, systematic framework where the goal is to reduce uncertainty systematically. So we don't jump, we're not too eager about trying to rule out hypotheses. We want to be smart about reducing that uncertainty predictably and fast enough. That was all for today. Thank you very much for listening to this talk. You can reach me at these emails. I'm very excited about this topic. Would love to collaborate or talk to about this. You can reach me in LinkedIn. If you want to hear more about other projects I have and workshops that I gave on this topic and more, you can scan the QR code. That will take you to a website with more information. Thank you.
Thank you. We have time for a couple of questions.
Nice.
I see that some of you have managed to get into the questions app. If you haven't, have a look for yourself. questions.gaia.fish. And there you will be able to post your questions, and our moderator Hannah will have a look at them and see if they pass the test. So the first question, how can teams effectively document and share their individual bags of tricks to avoid siloed knowledge?
I would maybe question the premise.
Yeah.
The whole point is trying not to rely too much on these bag of tricks. The whole point is that I would like to go to a junior that has no experience and say, hey, why don't we try following these things instead?
Yeah.
So it would lessen the need for sharing this type of symptom to root cause ideas. Having said that, if whoever asked this really wants to know my opinion on this, usually people post papers about this. Like if you search for bag of tricks CNNs, you'll probably find some articles on like 30 different things that you check, or like especially reinforcement learning. I used to work with reinforcement learning, and I remember great resources on like, if this happens, it's probably that. If this happens, check that this didn't happen, right? So maybe something like that, so you even help people outside your organization.
Yeah, okay. I really appreciated your reference to the medical side. It's a very good sort of parable and a good way to explain how you're thinking. It's also a very good bridge to the next talk, but that's a parenthesis.
Nice.
The next question is on the same theme, actually. I work with a lot of clinicians. They do actually rely on availability bias as a proxy for the prevalence of different types of issues. Having a realistic view of the prevalence of different types of issues is a key feature of an expert. Is that not also true for machine learning practitioners?
Absolutely. And this touches on a tricky topic, which is base rates. What I wish we had is like a comprehensive study on base rates. We kind of have that, at least like segmented by parts of the pipeline. You can find base rates about types of bugs you get at different parts. And no surprise, pre-processing is, just like I said, the one where you have the most bugs and the highest chance of having silent failures. Still, I mean, since we don't have that, availability bias is a tricky one to use. Like I said, if you don't have anything else to do, if you can't run any cheap tests, perhaps that's the way. But I assume that maybe whoever wrote that question runs cheap experiments first. Like they wouldn't just, like the thought experiment that I said, they wouldn't just go like, yeah, 3 months ago, meningitis, that's probably what you have, right? They would, if they use a little bit of availability bias, that's still after the groundwork of cheap experiments that gather a lot of information.
Brings us to the next question. Any thoughts on how I can set up an agent, for example in Claude, to do the initial cheap tests?
I'm working on that.
Okay.
I'm trying to work on that. That's surprisingly tricky, because at least the problems I'm facing is that you can give the information, you can give the instructions, but it seems to have such a strong prior for doing things differently that sometimes it just doesn't follow the instructions. And I say, hey, Claude, why don't you do that? And it's like, oh yeah, the instructions actually say that I should do that instead. So why didn't you do it? So yeah, work in progress, I guess, is my answer. That I don't have an answer that solves the issue yet.
Yeah, quite a few questions in here actually. Have you tried using the cheap tricks in a test-driven development? And if so, what was the effect on how many bugs you had to solve in the long run?
I don't understand the question.
Okay.
Can I read it?
Yeah, sure. Have you tried using the cheap tricks in a test-driven development? And if so, what was the effect on how many bugs you had to solve in the long run?
Whoever asked that question, stop me if I'm going in the wrong direction. So I can give some thoughts into what I think about TDD, at least, and how this relates to debugging. So I see debugging as machine learning debugging, but debugging in general as having three major parts. There's the preparation part, which is everything you do to your code base before you get a bug. Those are the actions you take to minimize the chance of getting a bug. And if you do get a bug, they will hopefully put you in the best position to even debug the thing that you're looking at. Then there's the active part, which is, I guess, what we discussed here, at least for these types of bugs where the symptom doesn't tell you where the root cause is. And then later the reflection part, where after you found the root cause, you can reflect on what other measures should I be taking in the preparation phase to stop this from happening again. Now, TDD would come in the preparation part, but TDD is an extreme part of a spectrum here, which I think of like there's a U-curve when you plot time spent on preparation versus time to deliver the project. If you don't prepare enough, if you have no tests, if you have no nothing, you just write code and then you run it, it's going to take a long time to deliver because you'll have a lot of bugs. And because of that, you'll spend a lot of time in debugging, so time to deliver is compromised. The other aspect, the other extreme, the time to deliver also increases because now you're spending too much time preparing. You will have fewer and fewer bugs, but the goal is usually not optimize developer experience. It's to minimize time to deliver. So there's a sweet spot of preparation that is very project specific. I see TDD as probably on the extreme part of the spectrum where you will get way fewer bugs, but in terms of like time to deliver, I'm not convinced that it's the best approach. I see more, for instance, if you have small functions with single clear responsibilities, well named, following best practices, if you do that to all your functions and some of them still are complicated, test those, maybe even TDD those. I'm all for that. But TDD as a whole concept, I see it as perhaps not optimizing time to deliver. Personal opinion. I apologize if whoever asked this question had a different direction about the question.
Thanks. Our time is up. The next talk will begin at 11:15, and we want to say thank you to Juliano with a little gift, which is in our... I'm going to go down and pick it up, actually. 1 second. From the city of wind and rain, of course. Thank you so much
Thank you
for your talk. Good to have you.